In this slide and onward, we will have an example for finite divided difference. Basically, we will try to predict the derivative of a function using the finite divided difference approximations like backward, forward, and centered difference methods. So this problem has this function in fourth order polynomial, and we will use x equals 0.5, and using a step size of 0.5 we will find the forward, backward difference approximations and center difference approximations of the first derivative. And also we will repeat the results with by reducing the step size to 0.25 to make an evaluation of the results to see how the accuracy changes. And the first derivative for the accurate result, or the true value, is this, basically the derivative of this. And the function value for 0.5 is this value. So we will use this as the true values. This is the true value. True value, true derivative. Of course, we may not know this for other functions, and that's why we need the finite divided difference approximations. But for this question, let's assume we know the exact value as well to make a comparison. And for the solution, as it says, we will start with h equals 0.5, and for xi is 0.5. Because step size is 0.5, xi minus 1 is simply 0.5 minus 0.5, because h is the difference between them. Xi minus 1 is 0 then, and xi plus 1 is simply addition of the step size to xi, which gives us 0.5 plus 0.5, which is equivalent to 1. And the function values for these, f xi, we can just simply write them here, and this is 0.925. xi minus 1 is 0, that's why f0 is actually here also 0.5. The function value for f0 function value is 1.2, and for f1 the function value is 0.2 by writing them here, finding the true values. These are the true values, and we need to use these to find or predict the derivative. Let's use forward difference first. Forward difference. I will not write the function, but I will just write the values. So it is the first derivative, 4.5, is equivalent to forward, because its forward difference is xi plus 1 minus xi minus 1, and these are the function values. So f1 is xi plus 1 over here. So 0.2 minus 1.2, simply 0.2 minus 1.2 divided by 0.5, which is actually here 1.2 is the smallest, xi minus 1, so we have to be careful. We will subtract f xi plus 1 from f xi, so 0.5, the function value of 0.5, which is this one. So this is not 1.2, but this is 0.925, and that's why the bottom part is h, so it is still the same. And for this, h is step size 0.5, and the result is minus 1.45. And here we can calculate the percent relative error for the true value is equivalent, and we can calculate it as the absolute value. So minus 0.925. Sorry, we will use the true value here, and true value, we said that the derivative true value is 0.9125. 0.9125 minus the predicted value. You can see we predicted 0.91 as 1.45, which is far away enough to say that this is not accurate. But let's see with the normalized error divided by minus 0.9125, the true value, times 100 is equivalent to 58.9%. This is very large. You can see it's more than the half of the result error. So let's check backward difference. Again, we will predict 0.5 xi, but this time we will use xi minus 1. And we have to be careful again, xi minus 1 and xi. So the function values of these. So 0.925 and 1.2. And here, so fxi, which is 0.925 minus fi, fxi minus 1, this value, 1.2, divided by the step size, 0.5. This gives us minus 0.55. And from here, the epsilon t, the relative error, with the true value, again this one, 0.9125 minus 0.55 divided by here also minus 1 divided by minus 0.9125. The result should be the same, even though I made a mistake of sign. I calculated correctly, and the result here is 39.7%. Slightly better than the forward difference because it was 58, but these are actually, both of them are big enough to say that these are not accurate. And for the center difference, the result is the difference between fxi plus 1, this value, and fxi minus 1, this value, 0.2 minus 1.2. 0.2 minus 1.2 divided by the step size times 2. That's important. Here the difference is between I minus 1 to I plus 1. There is I between them, and the differences are two time steps. So, and this is time step is 0.5. That's why the bottom part is 1 actually. And the result here is minus 1. And you can see this is very close to this one. So as expected, center difference gave a better result actually. And if we can see that from the epsilon t, or the error value as well, again the true value minus 1 divided by minus 0.9125 times 100. This is only 9.6%. Please look at the differences. These are very big, but this is below 10%, which is nice. Actually, this prediction is very good. So this simple question even shows the effectiveness of center difference, how accurate it is. And so further, now in the next slide, we will increase the step size, and we will see this will have much better approximation with this, because we know that the reduction of error is quartered when we reduce or halved the step size for this, but these ones are actually just halved again, linear. So this will be much more smaller. We will see that in the next slide. In this slide, we will solve the example 4.4, which is a fourth order polynomial, and we will try to find the first derivative, and we will do that by reducing the step size from 0.5 to 0.25. So we will halve the step size. So now step size is 0.25. Then Let's calculate xi again. Xi is 0.5. We started with it according to the problem. And if we use the step size, subtract it from xi, xi minus 1 is just 0.5 minus 0.25. It is 0.25. And xi plus 1 is actually summation of 0.5 with the step size 0.25, then it's 0.75. And the function values of true function are, for this again, 925, xi minus 1, so f 0.25 is 1.10351563, and for f 0.75 the result is 0.63632813. So let's calculate the forward difference. For the forward difference, f prime 0.5, we want to calculate this or predict this actually, and it is just the difference between xi plus 1 function, this, and xi function value, this, 0.925 to 0.63. Let's write it down, or actually from xi plus 1, 0.63632813 minus 0.925 divided by the step size. This is important. This is step size here. Now it is 0.25, and the result is minus 1.155, and the relative error, I'm not going to write the details, just the result, 26.5. Remember, this was above 50% when we use a step size of 0.5. Now we are using half step size 0.25, and the error reduced to half of it, 26.5%. We will summarize this in the end as well. Let's check backward difference. For this, again, f prime 0.5 tilde is equivalent to now xi minus 1 function value. The first one is xi function value. It is 0.925 minus f 0.25. It's 1.103515563, as you see here. This one divided by 0.25, and these actually the step size 0.25, that's why. And if we write the result, it is minus 714, and the relative error with this is 21.7%. Again, the error reduced because the true value was actually about 0.91 something, and you can see we are approaching it in a better way with these. Let's check the center difference. f.5 tilde is equivalent to now xi plus 1 minus xi minus 1, but the function values, let's write them down. 0.63632813 minus 1.103515563 divided by the step size times 2 again, so it is 2 times 0.25, which is 0.5. From here the result is 0.934. This is very close to the true derivative value. That's why the relative error becomes 2.4%. It's reduced dramatically. You can see it's very accurate, 2.4. So this shows the effectiveness of the center difference for finding the accurate result of the derivative. And So what we did is we used forward and backward, and we reduced the step size to its half, and halving step size resulted in the halving of the error. So it halved the error. For forward and backward. Approximations or find differences. For 0.5, if you remember, h is 0.5, then for the forward, the error was 58.9%. For the backward, it was 39.7%. We already calculated this in the previous slide. And in this slide, we calculated for 0.25. And these are, you can see, 26.5% and 21.7%. Almost half of the difference. I mean, from here to here, almost half, you can see. This is here, especially exactly the half for the forward. 58. Sorry. From 26 to 58. Half, almost half, from 39 to 21 as well. It cannot be exactly half, but you know, about half anyway. So let's check the halving of step size for center difference. Actually quartered the error as expected for center difference. And we can see that for H is 0.5, it was 9.6% the error, and when we reduced it to 25, it becomes 2.4. So it's almost 4 times smaller, quartered. It's very, very small, very accurate. And compared to forward and backward, you can see these, according to these results, these are very small, much smaller as expected. This is expected. And as we said earlier, if we have the values of previous and the next steps, just use the centered difference approximation because it gives much better results. And try to reduce step size to have better approximations of the difference as well. That's important. And with the centered difference, it's the reduction is much more. So with this, we conclude this example.